equilibrium. So I'm sure you guys can see the screen, and today we will learn about chemical equilibrium, and we will discuss 4 topics related to chemical equilibrium. And the first one is, let me just grab my laser pointer. All right. So the first one is chemical equilibrium and its type. We will discuss that how many different types of chemical equilibrium are there, and what do actually we mean by chemical equilibrium. And the second lesson for today will be chemical equilibrium and equilibrium constant expression. So this is the equilibrium constant expression that we use for chemical reactions. And this is the way to represent the equilibrium constant. So we will see that there are certain rules when we write these chemical equilibrium constant expressions. Another topic for today, which is related to chemical equilibrium, is Chatellier's principle. And we will see that what Chatellier's principle is, what's its definition, and how it is used in industry and in other aspects of life. And the fourth topic for today will be factors affecting chemical equilibrium, because, you know, little change in equilibrium, whenever we have a system at equilibrium, and if we disturb it, you know, by changing different parameters, it is affected. So we will see that what changes can affect a system at chemical equilibrium. So this is our lesson for today, and I hope you enjoyed today's lesson. So let's begin. So we are starting from lesson 1, which is chemical equilibrium. And here we will discuss what chemical equilibrium is and what are different types of chemical equilibrium. So chemical equilibrium is a fundamental concept in chemistry that describes the balance between forward and reverse reactions in a chemical system. So you must know, you know, by now that we have a forward reaction and a backward reaction. So whenever a chemical reaction take place, it is always reversible, right? So we have a forward reaction and we have a backward reaction that we will see in a moment. So in this presentation, we will explore the principles of chemical equilibrium and its different types. So chemical equilibrium, there is a misconception about chemical equilibrium. Most of the students, they believe that chemical equilibrium is an equilibrium, is a state where the amount of reactants, they become equal to the amount of products. And we have, for example, we have 50 grams of reactants. So it means that we will have 50 grams of products. So that means that the reaction is balanced now, and we can have a chemical equilibrium condition, but that's not correct. So chemical equilibrium occurs when the rate of forward reaction becomes equal to the rate of reversible reaction. These two rates, they become equal, resulting in a constant concentration of reactants and products. So that is what chemical reaction, basically a chemical equilibrium is. So all reactions are reversible and reach a state of equilibrium. So let me use a whiteboard here. Let me take you to the whiteboard to explain this concept to you. So I'm sharing this screen with you here on a whiteboard. So let's start from here. For example, we have we have a reaction. We have a reactant A, and it is reacting with B, right? And it is a reversible reaction. So we use this symbol for reversible reaction. You know, we have this double arrow. It is used for reversible reactions, and it is producing C and D. Okay, so when the reaction is about to start, you know, when we start the chemical reaction, so we only start with reactants. We do not have any products. So we say that, you know, before the start of the reaction, we have, let's suppose, 50 grams of A and B, and we have 0 grams of C and D. This is when time is equal to 0, when the reaction, has not started yet. So in that condition, we have the concentration of the reactants is 50 grams, and the concentration of the products is 0 grams, right? So when time starts, when we start this reaction, so we say that time equals T. T can be any time, like 10 seconds, 1 minute. So this is a general term representing for T time. So what happens is that the concentration of the reactants AB, it starts decreasing, right? For example, from 50, it will become 40 grams, and the amount of the products, they will start increasing, and we will have 10 grams of the products. So as the time continues, so what happens is that the amount of the products, the reactants, they keep on decreasing. So from 40 grams, it may reach, let's say, 20 or let's say 30 grams. And the amount for the product, it will be around, let's suppose, like 20 grams. Yeah. So it is keep on increasing the reactant, the concentration of the product, and the concentration of the reactant is keep on decreasing as the time continues. So at this point, some reactions, they gain equilibrium. So what happens is that this reaction, the backward reaction, it will start, going in this direction. And the forward reaction, it is going in this direction. They will balance each other, and the reaction will appear to stop. The reaction will be continue, but the concentrations, they will not change anymore, right? So, we started from 50 and 0. So we can write here 50, 0. Then we end up at 40, and then 10, and then 30 and 20, right? So you can see that the concentration of the products, it is decreasing, the reactants, and the concentration of the products, it is basically increasing, right? So this is the term that I used for increasing, but you can see that we have 0, so we have 10, and we have 20. So we can write the symbols here. It is decreasing, and this is increasing, right? So at this point, the reaction, it achieves equilibrium, and we say that this point is, at this point, the reaction is at equilibrium. So you can see that the concentrations, they are not changing anymore. So the concentrations are balanced, and the rate of the chemical reaction of the forward reaction and the backward reaction is balanced. So we can write here forward reaction Rxn, it becomes equal to, reverse reaction, right? So this is the condition where our equilibrium is achieved. So this was the explanation for achieving chemical equilibrium. So now let us go back to the slides and continue reading from there. And after some time, if I wanted to explain something on the whiteboard, we will come back to our whiteboard. Okay, so as I said, all reactions are reversible and reach a state of equilibrium. So this is an excellent example for how the equilibrium takes place with time. As you can see here, we have a reaction. We have N2O4. We have dinitrogen tetraoxide, which is colorless. And we have nitrogen dioxide, which is brown. So it is a macroscopic view of equilibrium, which you can practice, online. We have different videos and different simulations available on the internet. So as you can see here that we have primarily the molecules are of N2O4. So the reaction mixture consists mostly of colorless N2O4. So the reaction is not started yet. So you can see here the time is 0, right? Just like I explained the example on the whiteboard. So as the time starts, when we start the reaction, so as the N2O4 decomposes to NO2, the mixture becomes pale brown. And here you can see that we have started, appearing the nitrogen dioxide molecules. So here we cannot see any nitrogen dioxide molecules, but here we have 3, right? Here we have only 1, and here we have 3. So since it is brown, so you can see the color change from colorless bottle. The reaction is changing. The product is developing. The product is appearing, and we can see here the color change. So now when we have, when 20 minutes have been passed, so now we can see, look at this dark color, right? So now we have lots of nitrogen dioxide molecules in this bottle. So we have the brown color deepens as more dinitrogen tetraoxide decomposes and more NO2 is produced until the color reaches a maximum at equilibrium. So now what happens is that here at this position, at this instant, we have achieved a chemical equilibrium, and we have this dark color, and where the rate of the forward reaction is equal to the rate of reversible reaction. And this system, this reaction, it achieves equilibrium, right? So this is how we can visualize our equilibrium reactions. Okay, so again, this is a fundamental, definition, and I urge you to understand this and do not make a mistake when writing about chemical equilibrium. So it is not about the quantity; it is about the rate of the reaction, right? So at chemical equilibrium, reactant and product concentrations are constant. They are not necessarily to be balanced by mass, right? The products and the reactions, they should not change anymore. What do we mean by constant? Something which doesn't change, because a change in one direction is balanced by a change in the other as the forward and the reverse rates become equal. So we can write at equilibrium, rate of forward reaction, it becomes equal to the rate of reversible reaction. So this is how equilibrium is established, and this is how we define it, right? And this example or this type of equilibrium is called dynamic equilibrium, because the reaction is not completed yet. The reaction never gets to completion. Only the rates, they get balanced, at different concentrations. So this was our first topic. Now we are entering our second topic. So we will take about 15 minutes on this, which is equilibrium constant. That how do we write equilibrium constant expressions for chemical reactions? This is very important, in chemistry. During your exams, we may see lots of questions on these topics. So for the reaction that we studied, equilibrium constant is a ratio of the forward reaction to the reverse reaction, right? So the forward reaction is mentioned with NO2 square, and the reversible reaction is denoted with N2O4, and we do not have any coefficient here. So why do we have a square here? So let me take you back to the whiteboard and let me show you that how we write these chemical constants for these chemical equilibriums. All right, so here we have the ratio of the rate constants, which creates a new constant called chemical equilibrium constant. And we can see here that K equals forward equals, divided by a reversible reaction. So we have NO2 square and we have N2O4. So again, here we can see that if you look at the colors which are representing the chemical reactions, and what happens is that here we have a blue color, and then here we have a red color. So this is the product, and this is a reactant, and this is a product. So here we can see that we have lots of reactant. The blue molecules are in a higher quantity, but the products, they are in lesser quantity, right? So for this reaction, we have a equilibrium constant expression is 0.020. So now if you look here, if we have lots of product and if we have very few amount of the reactant, so the equilibrium constant will be very high. So you can see here, this is our reactant, and this is our green is our product. So here you can see that we have lots of product. So if we have a lots of product, we have a higher equilibrium constant. And if we have a lower product, the equilibrium constant will be very low. And if our equilibrium constant is very close to 1, it means that we have equal number of reactants and the product, right? So we have, black is representing the reactant, and the green balls, they are representing the products, right? So we have equal quantities of reactants and products. So that is when we have equilibrium constant, which is near to 1. So if we look at the chemical equilibrium constant, so we can predict that how will the reaction it will proceed, right? From in one way or the other. So this is how we basically predict that how the reaction will take place. Okay, so now we have two more points. So we have equilibrium constant expression, and then we have a quotient. So what is a quotient? Quotient is, an expression when the equilibrium constant is not, when the reaction has not achieved the quotient. So quotient is a value where a reaction has not achieved a chemical equilibrium, and we just write the values anyway. So what do we do is, if you look here, we have we have 1 mole of N2O4, which is dinitrogen and tetraoxide. And here we have 2 moles of nitrogen dioxide. So what do we do is that this is our product, this is our reactant, So we write the product on top and the reactant at the bottom, and the moles are taken as are written as a power. So if you look here, we have 2 moles, right, on this side. So we write 2 as a power here of NO2. So this is how we write the reaction quotient, or the quotient expression. And when we put values here, when we put concentrations in these brackets, so when we calculate it, we will see that if the reaction achieves the chemical equilibrium or not, right? So this is how the chemical equilibrium is achieved. So again, so if we look here, so at equilibrium, this Q becomes equal to, which is Q is quotient and K is equilibrium constant. And this at equilibrium quotient becomes equal to our equilibrium constant expression. So if you look at this graph here, so we have the concentration, it is decreasing, which is N2O4. This is our reactant, and here this is our product, right? NO2, and the concentration of the product is increasing. So at this point, when the equilibrium is achieved, we say that Q becomes equal to K. So I hope this point is clear, and it is very useful. And most of the times you will see questions related to this topic. So now we have some of the questions here that we can practice. We write the reaction quotient QC for each of the following reactions, N2O5 and NO2 plus O2. So let's see if we can launch a whiteboard here and see that and practice these questions on a whiteboard. It's not here. I will have to share the screen for the app. Yeah. I hope you can see the whiteboard. So we are about to calculate the equilibrium constant expression, right? So let me just, I think this is not working. Let me try again. Okay, so if we have first question, N2O5, so we can write here N2O5, and we have a reversible reaction with NO2. We can write here NO2, right? And we have another product in this reaction, which is O2. So this is our chemical equation. And now we want to write quotient for this reaction. So how do we do that? So we have just seen that we need to write the products. So these are reactants. And these are our products. Right? So the products, they will go on top, and the reactants, they will be at the bottom. They will be as a denominator. So we write QC equals concentration symbol NO2 and O2, right, divided by N2O5. So this is the equilibrium constant or quotient for this reaction number 1, right? So now we have another problem that we will need to write the equilibrium constant for, and that is sodium when it reacts with water. So Na plus H2O, when it reacts reversibly, so water is in liquid form, right? And sodium is in solid form, in a solid state. And then we have NaOH, sodium hydroxide. This is in aqueous. Plus, we have H2, which is a gas. So another important point is that whenever we are writing this quotient for chemical equilibrium, we do not write pure solids, and pure liquids. So they are not included in the quotient or the equilibrium constant expression. So now we have a pure solid. This is a pure solid. So we will not include this in our quotient. This is a pure liquid. So this will also not be included in our quotient. So how will we, what will be our quotient then? QC for this reaction will be equal to just NaOH times H2. That's it, right? Because we do not write, let me write it here so that you guys can remember. Do not write pure solids and pure liquids in QC or KC expression. Yeah, so that's it. So these were some of the questions that we practiced. So now let me take you back to the presentation, and you guys can note it down, the other questions that I'm displaying. You can try for this one, the third one. I solved the first two, and you can solve the third one, which is C3H8. It is a gas, and O2, it is also a gas, and we have carbon dioxide as a product, and we have water as a product. But if you look here, water is not a liquid, is not in a liquid state here. So all these entities, all these reactants and products, they will be a part of your equilibrium quotient. Okay, so this is how we write equilibrium constants. And if you look here, if we have quotient is small, and the equilibrium constant is greater, so what will happen? The reaction will proceed towards the right-hand side so that these two can become equal. And if for a reaction we have QC is in greater quantity and KC is in a lower quantity, so the reaction will be transferred. It will move toward the backward direction so that we can equal these two and equilibrium is achieved. So this is very important for industrial point of view, and whenever we want to achieve chemical equilibrium in the chemical industry. So by looking at the values for the QC and KC, we can make changes to our, reactants and products, and we can make the reaction shift either in, forward direction or in a backward direction. So again, when we compare the values of quotient with K to determine the direction in which a reaction will proceed toward chemical equilibrium. So you need to remember these three conditions. These are really important. So the first one is QC. If our quotient is less than KC, just like it's here. So QC is less than KC, more products will form. The reaction will proceed in the forward direction so that it can achieve a chemical equilibrium. If we have a second case, if we have a QC, which is greater than KC, which is this case. So here QC is greater than the KC. What will happen? More reactants will form. The reaction will be in the reverse direction, right? And if QC is equal to KC, when we have these two values equal to each other, so the reaction will be at chemical equilibrium, and no change will take place in both the reactants or the products. So if you look here, it is written here, no net change. So, you can get these questions as multiple choice questions. You can get these questions as, critical response, or you can get these questions as extended response questions. All right. So now we are entering our third topic for today, which is Lee-Chatelier's principle. So it is a highly useful principle which is used in chemical industries related to chemical equilibrium. And let's see what do we have to discuss in this one. So let's start from the definition first, and it says that Lee-Chatelier's principle, when a chemical system at equilibrium is disturbed, it retains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. So it means that when you have a reaction at equilibrium, when we have two reactants and products, their rates are balanced. So if we disturb the chemical equilibrium, so the reaction will change itself in order to reestablish the chemical equilibrium. So let me take you back once again to the whiteboard and see. Let me explain this point to you. Okay, so we have a reaction which is A plus B, and it is reacting with each other, and we are getting the products C and D. And so this reaction is at equilibrium, right? So equilibrium. All right. So let's suppose I disturb this chemical equilibrium. At the moment, the rate of forward reaction is equal to the rate of reverse reaction. So now let's say I add A, adding A. So I am increasing the concentration of A. So what will happen? So if the concentration is increasing on the left-hand side, this is our left-hand side, this is our right-hand side. So what will happen? The reaction will move to the forward direction, and more product will be formed so that we can minimize the change of adding A, right? So this is case one. Now we have case two. Now I increase the concentration of the product. Let's suppose I add D. So adding D which is a product. What will happen to the chemical reaction? In which direction the reaction will proceed? It will proceed to, in the reverse direction, in the backward direction. So we have A plus B, and we have C plus D. So if I add D, if I increase the concentration of D, the reaction will move towards the left-hand side, right? And more reactants will be formed. So it will favor reactants. And this reaction, here we are favoring products. If we add something to the reactants, products will be formed in a greater quantity, and if we add products, so the reactants will be formed, right? So this is how the chemical reactions, they readjust themselves to on a newer concentration, and equilibrium is reestablished, right? So let's go back to our presentation and see what else do we have in this topic. Okay, so the industrial application for the Le-Chatelier principle is that production of ammonia, ammonia NH3. This is ammonia NH3. It is a really important gas, and we have lots of industrial uses to ammonia, and we make lots of chemicals using ammonia. So what happens when we combine H2, which is a hydrogen gas, with nitrogen, which is N2, and we have a compressor here. So these two gases are compressed, which means that they are pressurized. The pressure is increased on these two gases. So when we increase the pressure, then they are sent to the reaction chamber with a catalyst bed. So catalyst is something which speeds up the chemical reaction by lowering the activation energy. And then what happens is that we have ammonia and NH2, H2, and N2. So we have reactants and we have products, and then ammonia is condensed and it is changed into a liquid form, and we get pure ammonia. So what is happening? So how can we apply Le-Chatelier's principle to get more ammonia, right? So if we remove this ammonia, right, from this side, so the reaction will proceed in the forward direction. So they will react more quickly, and we will get ammonia in greater quantity. So in industry, so whenever we are making ammonia, we continuously remove the ammonia so that the reaction can keep on going to the forward direction, and we get lots of ammonia. So the next point, we keep increasing the concentration of H2 and N2. So when we increase the concentration of hydrogen gas and nitrogen gas, so we are changing the chemical equilibrium. So the reaction will also proceed in the forward direction to the right-hand side. And what will happen? The more ammonia will be produced. So this is an excellent example for the Le-Chatelier's principle, where we use more ammonia is produced by applying the rules of Le-Chatelier's principle. So now, in our last 10 to 15 minutes, now we will see that how the chemical equilibrium is affected. What are the factors which are responsible for affecting chemical equilibrium? So let's talk about the concentration. So when a system is at equilibrium, when we have the rate of the forward reaction, it is equal to the rate of the reverse reaction is disturbed by a change in concentration of one of the components. By components, we mean whether the reactants or the products. So it reacts in the direction that reduces the change, right? So if the concentration of A is increased, the system reacts to consume some of that component. If the concentration of A is decreased, the system reacts to produce some of it. Only components that appear in Q quotient can have an effect. So changes in the amounts of the pure liquids and solids cannot. So this is the point that we just discussed in the few slides back when we were discussing the equations on the whiteboard. I told you guys that we cannot have pure liquids and pure solids in a chemical reaction, right? So this is the final table, and let's summarize and see that how the chemical reaction it is affected, right? So the first one is concentration. So we have disturbance. We have three to four types of disturbances here. The first disturbance is if we disturb the concentration, whether on the reactant side or on the product side. Then we have a disturbance of pressure. We can change pressure. We can increase or decrease pressure. Then we have temperature. We can increase temperature or we can decrease temperature. And we have a catalyst added. So a catalyst, sometimes it will, enable us to achieve equilibrium quickly, but it affects the forward end reaction and reversible reaction with the same manner. So let's talk about concentration. We have disturbance, then we have effect on equilibrium position, and then we have effect on the value of K. So if we increase the concentration and the forward reaction toward the formation of product, it will not have any effect on the chemical equilibrium K. If we decrease the reactant, the equilibrium will shift toward the formation of the reactant, and the value of K will remain unaffected. So now we have if another case in which if we increase the product, so the reaction will move toward the formation of the reactant. So more reactant will form and the value of K will remain the same. And if we decrease the product toward formation of product, so no effect on equilibrium constant will take place. Why? Because the reaction will readjust itself and the change will be nullified. So let's talk about the pressure now. So if we increase the pressure, we are decreasing the volume because they are inversely proportional to each other. If pressure is increased, so volume is decreased, or in another case, if we decrease the volume, the pressure is increased, right? So what will happen toward formation of fewer moles of gases? So the reaction will change, will move toward that side where we have lesser number of moles, and the effect on the value of K, it will have no effect on the equilibrium constant expression. If we decrease the pressure, in other words, we are increasing the volume. So what will happen to, on which side the reaction will move? It will move toward the formation of more molecules of gas. It will move towards the place to the side where we have more moles. And again, there will be no change in the concentration or in the chemical equilibrium constant. So now we have another case. If we add inert gas, so no change in volume, so again, there will have no change on the reaction. The reaction will stay the same, and it will have no effect on the chemical equilibrium. So let's talk about the temperature. So what is happening with the temperature? So if we increase the temperature, so by increasing the temperature, the delta H of the reaction increases, which is a change in enthalpy. And if it increases the delta H, if delta H is greater than 0, and it decreases the K constant of chemical equilibrium if the delta H is less than 0, right? So if we decrease the temperature, what will happen? The reaction will move towards where lesser heat is released. We are toward release of heat. So it will move toward the exothermic side. So so what will happen, how this change will affect the value of K? So here we will have increase in delta H if it is less than 0. And if it will decrease, the value of K will decrease if the delta H is greater than 0. Finally, by adding the catalyst, the reaction will stay where it was. It will not move anywhere. It will not move towards the left-hand side to the reactants. It will not move towards the right-hand side to the products. And there will be no effect on the value of K, right? So this is how we, study chemical equilibrium. And these were some of the aspects in which we discussed that how chemical equilibrium is affected. So for those of you who joined, later in the class, so let us quickly summarize the concepts that we studied in today's lecture. So do you have any questions at the moment? Yeah, Jose, no questions. Did you get it? Did you get it? Is it clear? Okay, that's great. That's great. So let's quickly go back and just summarize the entire concept. So in the reaction, we started with chemical equilibrium and its types, that what is chemical equilibrium. And we discussed that chemical equilibrium is achieved when the speed of the forward reaction, it becomes equal to the rate of the reversible reaction, right? So when a reaction is in such a condition where the rate of the forward reaction is equal to the rate of the reverse reaction, we can say that that system, that reaction is in a chemical equilibrium. And that is called dynamic equilibrium, right? So then we discussed the equilibrium constant. So what is equilibrium constant? It is the ratio of the forward reaction to the ratio of the concentration of the reverse reaction. So we write it like this. We write the product on top, and we write the reactants at the bottom. So if you look here in this reaction, so NO2 is at the top, which is a product, and N2O4 is at the bottom. You see, we have written it like this. So this is how we write chemical constant, chemical equilibrium constant expression, which is called K. So by analyzing the equilibrium constant, we can see that if the equilibrium constant is very small, it means that we have lots of reactant and there is very few molecules of the product. If the value of K is very large, that means that we have a very less amount of reactant and we have lots of products in the chemical reaction. And if the value is near to 1, that will mean that in such chemical reactions, we have equal amounts of reactants and equal amounts of products, right? And then we discussed the Lee-Chatelier's principle, which is that when a system is disturbed, when a chemical reaction at equilibrium is disturbed, it changes itself in such a way that the equilibrium is reestablished, right? And finally, we discussed that what changes, can impact the value of K and how the reaction will move towards the reactants or towards the products, right? So this was today's lecture. I hope you understood it. If you have any questions, you can leave them in a comment below. Thank you so much for joining.